So, all of you know we are discussing on the coordination compounds. Yes. Sir, do you have to write the practical which has been uploaded in the YouTube? Yes. Okay, it will be better if you ask it to Uday sir. I hope you have to write it, but the clear definition will be what the instruction. Have you seen the video? What instruction is given in this video? When I have talked to Uday sir, he have told that they have to write it, but from the video is any instruction is there? Sir, he does not reply to question in the e-portal. Okay, follow the chat box. On the next day, I hope you have to write it, but first of all we should be confirmed about that. I don't have the practical copy. Only you or more of than you? Shreya, only you have not the practical copy or other it? Because of lockdown I am unable to buy it. Oh, বুঝেছি. So now first of all you should be confirmed that if you have to write it. Payal, Orpita, Meghna, they are far apart from school. Okay. What Sankorson is typing? I know you have. Those having the practical copy and those who can understand how to write it, they may write it. Okay, and how to write you have already written in the class 11 in the same way. That is how to write the test for organic and the inorganic in the same way, because there was just the preliminary test was there. Okay. Okay, so later on you follow the chat box, that means the e-portal. If he put any remarks on that, or on the next class you may ask to the Uday sir, and I also ask Uday sir that what is the instruction to you. Okay, then I will tell you about that. So wait for the next class, and those having problem he follow the e-portal, because if it is possible then I ask Uday sir, then I will reply in the e-portal. So I hope you have to write it, and for writing it is uploaded, not to see only. Okay. So moving to the text. The last day what we have discussed, that is the bonding in metal carbonyl. Okay. Metal carbonyl complexes. The important areas was the synergic bonding. I hope you have studied these already. Synergic bonding. Bhaswati. Check your network connectivity and audio jack. Except you, all can hear, I think. No one can hear. Now you can hear. Hello. Now you can hear. Yes, okay. So we have discussed on the metal carbonyl bond. Today I will discuss on the topic, that is what is organometallic. Now from the name organometallic, that is a relation between organic compounds and metal. Okay, so this type of compounds having a direct relationship between the organic compound, that is carbon, and metal. So a direct bond is there in between the carbon of an organic compound and metal. So today's topic is on the organometallic. That is a direct relation between carbon and metal. This type of complexes where a direct relation is there in between the carbon and metal is called a organometallic and organometallic compounds. One example that is RMgX, alkyl magnesium halide. Already you have used it, RMgX. This is a very basic example of organometallic. Now R is the alkene part and magnesium is the metal. So in this type of compound is called Grignard reagent. Yes. So in this type of compound, here you can see the carbon and metal bond. Yes. So this type of compound is called the organometallic compound. Now next is the classification of organometallic compound. Classification. Okay. Now in classification, first one, that is number 1, that is main group elements. Main group elements, when they form compounds, that is organometallic compound, is called the main group elements organometallic compound. So one example of this type, that is main group that is formed by lithium or boron or lead, etc., are main group, but that is CH3Li, CH3 whole thrice B, etc. These are the examples of main group elements. Here lithium, beryllium, boron, these are the main group. Next one, that is D and F block element. D and F block elements are there. In D and F block element, that is ferrocene, tetracarbonyl nickel, FeCO whole 5, Na, CO whole 4, etc. These are iron, nickel. These are the D and F block elements. So when they forms the compound, that is D and F block compound. Next one, on the basis of bonding pattern, that means a sigma bond or pi bond. The connectivity between metal and the ligand is sigma bond or pi bond. Next classification is on that. That is, first of all, when metal bonds a sigma bond, the classification name is that the sigma bonded organometallic compounds. Classification based on bonding pattern. Okay. So first one is sigma bonded. Sigma bonded organometallic compound. This example is the Grignard reagent. Already we have told it. I have told it. Then diethyl zinc. These are the tetraethyltene, these are the sigma bonded organometallic compound. Okay, so RMgX, that is Grignard reagent, tetraethyl zinc, these are the examples of sigma bonded. Next one is pi bonded. Pi bonded is that Zeise's salt, that is K PtCl3 C2H4. Zeise's salt, ferrocene Fe C6H5 whole 2. These are the examples of pi bonded organometallic compounds. So in this way we can classify the organometallic compounds. Okay. Now next, what is the importance or the significance of organometallic compound? Now the organometallic compound, as the metals are electron deficient, so it is used as a catalyst in specifically, it is used as a catalyst specifically in different reaction, in organic reaction and also in the inorganic reaction. Wilkinson catalyst PH3PRHCl. Okay, it is a complex of rhodium. It is called Wilkinson catalyst. Wilkinson's catalyst. So it is an important organometallic compound which is used as a catalyst in organic, that is in halogenation reaction. Okay, in organic synthesis you have already come to know about, that is organolithium or organomagnesium, that is Grignard reagent, are already used to react in carbonyl compounds. Next, anti-knocking agent tetraethyl lead, these are used as anti-knocking agent. Okay, and in the metallurgical process we have come to know about the Mond process, that is the separation of nickel, that is purification of nickel from its impurities. Here also we have used the organometallic compounds. Okay, in medicine, that is in surgery, and also in agriculture, that is preparation of the fungicide. The here fungicide, that means the compounds of zinc, and also in case of chrome manganese, and sometimes it is that of the mercury. These are used as in agricultural field. Okay, so these are the applications of organometallic compound. Next, last day I have told you about the stability constant. Okay, and the stability constant, that is stepwise stability constant and overall stability constant. What is this? That is, when a compound is formed, it is formed by step manner. That is, suppose Ml, M is a metal, stability constant. Stability constant here, that is overall stability constant, overall stability constant, and stepwise stability constant. Stability constant, it is symbolized as Kn, and it is K1, K2, K3, etc. It can see that if M, a ligand, a metal, forms Ml, then in the second step Ml plus L forming Ml2. In the third step Ml2 plus L forming Ml3. In this way Ml n minus 1 plus L forming MLN. Okay, so in this step the stability constant is K1, it is K2, it is K3, and this is Kn. K1 is equal to concentration of Ml by concentration of M into concentration of L. So in this way it is found that K1 into K2 into K3, it is equal to Kn, that is the overall dissociation, overall stability constant. Okay. Kn is sometimes it is symbolized as beta. Okay. Next one is the factors affecting the stability of complex compound. Factors affecting the stability of the complex compound. So, stability constant, stepwise and overall. What is the importance of this? It is from the kinetic term, that is we know already that there are two parameters, one is thermodynamically stable and another one is kinetically stable. In this way we can tell that which one is kinetically stable and which one is thermodynamically stable. From the kinetic term it is due to the kinetically stable product. Next one, that is stability of coordination compounds. What are the factors? What are the factors under which the stability of the coordination compounds depends? So, number one is the metal ion. In which respect the metal ion is responsible? Number one is size and charge. So, the charge by radius ratio is very important here. Charge by radius ratio is again important here in the purpose of stability of the coordination compounds. Okay. Okay. So, first one is the metal ion. So, first one is the metal ion, as is the metal having very small size and charge density is higher, then the complex will be much stabler. For one example is there, the cation, that is Cu2 plus, nickel 2 plus, cobalt 2 plus, iron 2 plus, manganese 2 plus, in +2 oxidation state the radius is different, that is Cu2 plus, that is of 69, nickel 78, cobalt 82, iron 83 and manganese 97. So, as the radius varies, that is from left to copper in the right and manganese in the left. So, as the size of the cation is decreases, its charge density will be higher. Okay. So, the compound become more stable. For this reason, compound of copper is more stable than that of the manganese in the same oxidation state. So, the order of the arrangement of cations, that is having same oxidation state. This is called Eyring-Williamson's order. Eyring-Williamson's order is the order of arrangement of the metal ion of same oxidation state with respect to the complex formation or the stability of the complex. Okay. Next one is the nature of the ligand. Next one is nature of the ligand. Number 2, nature of the ligand or ligands. Okay. If the basicity of the ligands is higher, then the complex form will be much stable than that of the other. That is one example of that. If a cyanoligand is there, and water, that is aqua ligand is there, then with the same cation, that is if we take nickel, okay, Now, the compound, that is NiCN whole 6 and NiH2O whole 6, these compounds will be of higher, that is of more stable than that of the previous, that is of aqua complex. So, it is the nature of the ligand, that at the basicity of the ligands is higher, the complex is much more stable than that of the less field strength wise metal. Next one is the presence of chelate ring. Presence of chelate ring, already I have discussed on this, that is, as the chelate is a ring structure. So, it is already it is stable one. So, as chelate is a ring structure, already it is stable. So, presence of chelate ring here is the important term. So, if a compound is forming some chelating ligand, that is the bidentate or tridentate ligand, then the compound will be more stable. For example, NH3 6 times 2 plus and EN 3 times 2 plus. This compound is much more stable, and this stability of this ion can be predicted by using the overall stability constant or stepwise stability constant. Okay. So, as it is a chelate ring is there, it is stable than that of the monodentate ligand. Next one is there, that is macrocyclic effect or macrocyclic compound. Macrocyclic compound. Okay. Now, what is macrocyclic compound? You have come to the knowledge that hemoglobin and that of the chlorophyll, these are the biological origin, but a cage like structure is there, which is called porphyrin ring structure, where some pentagons are there creating a cavity, and in that cavity the the metal that is manganese or sometimes iron in case of hemoglobin are trapped. So, in that case the stability of such kind of compounds are higher. So, macrocyclic compounds, it is due to the cage like structure of some cyclic ring structure which forms a cavity in their surrounding and trap the metal ion, forming a stable complex. So, these 4 are the important factors in the stability of the coordination compounds. Okay. So, first one is the metal ion, here charge and size. Next one is the nature of the ligands, presence of chelate ring, and last one is the macrocyclic compounds or macrocyclic ligands. Now, macrocyclic ligands, that is the one example of macrocyclic effect, that is in hemiprotein, that is the macrocyclic ligand, you can say the porphyrin ring. One example of macrocyclic ligand is the porphyrin ring, the the drawing of like that. Four pentagon alternate double bond is there, and in between these here is the cavity where the N plus is there. So, this is called the porphyrin ring structure. So, stability of the coordination compounds was done. Next, what is the application area of the coordination compounds? One example is that one is labile complex and inert complex. Labile complex and inert complex. So, when labile complex, that means the exchange of ligands is there, which is very frequent, then it is called a labile complex. One example of that, if suppose NiCl4 plus cyanide, it produces Ni4 cyanide, Cn4 plus 4 Cl minus. Okay. So, this type of complex which go frequent exchange of the ligand is called labile complex. Okay. An inert complex which does not change or which does not change the position of the or which does not exchange the position of the ligands is called the non-labile or inert complex. Okay. Now, I am moving to some questions. You have to answer it. If you cannot, then I will make it over. Write the IUPAC name of the compound. CO NH3 6 times Cl3. Make it CO NH3 6 times Cl3. Yes, Sankarsan is there. Hexaamine cobalt 3 chloride, yes, very good. Okay. And now I am moving to one different questions, that is the oxidation state of iron. Oxidation state of iron in this compound. What is the oxidation state of this compound? Because from this we will calculate the bond moment, the ground state electronic configuration, the excited state electronic configuration. So, this is a very important part with respect to the valence bond theory. +3, yes, it is also correct. So, this is how to calculate, just assuming it as X, and just remember the charge of the cations and anions, you will get it. Okay. Now, how many geometrical isomers are possible in the in some coordination entities? CO NH3 3 times Cl3, CO NH3 3 times Cl3. How many geometrical isomer, not optical? How many geometrical isomers? So, in NCERT you have to come with the general formula, that is Ma3B3. Now, for Ma3B3 type compound there are cis trans isomer, that is when the 3 ligands are on the same side or in a same phase, then it is cis, and when they are in different space it is the trans. Yes. So, we can find the 2 geometrical isomers, okay, for this type of compound, that is Ma3B3 type compound. Next, draw the structures of the optical isomer for PT En2Cl2, platinum En2Cl2. You have to draw the optical isomer. Okay. So, one is bidentate, so it is a octahedral complex. Now, for octahedral complex, there yes, Cl, can you draw it? Cl, Cl, they are DL pair or A pairs of isomer. So, this is the structure of the isomers, that is optical isomer, and here also then what will be the total number of isomers for this compound, that is including the geometrical and optical. Total number of isomers for PT 3, yes, because there is 2 from there and 1 from the which the 2 having the similarity in the structures. So, overall the structure will be 3, yes, transform will be similar from that. Next, write all how many geometrical isomers are possible for platinum, NH3 Cl, NH3Cl, pyridine and bromine and pyridine, geometrical isomer. Now, it is a general formula, that is M ABCD. Okay. So, for this type of compound M ABCD, we have to fixed one, that A, and we have to rotate other 3 A B C D, then M A, then in D C B, M A, that is B D C. So, these are 3 geometrical isomers for the compound, that is M ABCD. These are all geometrical isomers. Okay. So, today up to this, on the next day we will discuss for more example from that, and we will move to the next unit. Okay. So, bye everyone, and thank you for having with us.